The computers we use today have become more powerful through the miniaturization of semiconductors. However, the progress driven by Moore's law is approaching its limits, making further performance improvements harder to achieve. At the same time, many of the challenges facing society require enormous computational power and are difficult to solve even with today's most advanced supercomputers. To tackle these issues, Fujitsu is rising to the challenge of developing a groundbreaking quantum computer. Classical computers, in principle, use bits that represent a single value of either 0 or 1. Quantum computers, on the other hand, use what are called qubits, which can represent both 0 and 1 at the same time. This is a conceptual diagram of a qubit. When the arrow is pointing up, it represents 0. And when it's pointing down, it represents 1. However, a qubit can be in a state where the arrow is pointing in a tilted direction. When it is measured in such a state, 0 is observed 80% of the time, and 1 is observed 20% of the time. In this state, 0 is observed 30%, and 1 is observed 70% of the time. Since qubits can represent both 0 and 1 at the same time, adding more qubits increases the amount of information that can be handled exponentially, compared with classical bits. With 2 qubits, 2 to the second power is 4. The capacity increases by 4 times. 4 qubits is 2 to the fourth power. That's 16 times. 10 qubits is about 1,000 times, and 30 qubits can handle roughly 1 billion times the amount of information. Moreover, qubits also have wave-like properties. By utilizing wave interference, it is possible to obtain results. Therefore, quantum computers with large numbers of qubits are expected to solve problems that have so far been impossible for classical computers. To realize qubits, a number of approaches have been proposed for the highly versatile, gate-based quantum computing model. The superconducting method uses superconducting circuits operated at ultra-low temperatures as qubits. The diamond spin method uses qubits formed around impurities introduced into diamond. Other approaches include trapped ion, neutral atom, photonic, and silicon-based methods. Among them, Fujitsu is focusing on the superconducting and diamond spin approaches. For the superconducting approach, we are carrying out joint research with RIKEN. We are also working with Delft University of Technology in the Netherlands for the diamond spin approach. On the flip side, errors are inevitable based on the principles of quantum computation. One of the key points for development is knowing how to prevent errors. Just as musical notes dance across a staff, quantum computing follows a similar pattern, with qubits moving along the lines of a quantum circuit. The vertical lines and boxes on these horizontal lines indicate interactions with other qubits. Through these interactions, the calculation arrives at a result. However, as qubit interactions increase, errors also increase. Thus, in early-stage quantum computers, known as NISQ, calculations must be completed within the coherence time, the period before errors occur. The computing time available using the superconducting approach is merely 0.1 milliseconds. To address this, one approach is to have quantum computers handle difficult tasks, while classical computers handle the rest. By adopting this kind of hybrid computing, quantum computers can be put to practical use more quickly, expanding the potential of advanced computation including AI, and opening the door to new approaches. With the incorporation of error correction technology, researchers aim to enable quantum computers to perform long-duration calculations independently in the future. Specifically, what had previously been treated as a single qubit will each be replaced with hundreds or thousands of identical qubits. Even if one of them makes an error, the system can compare it with the others and correct the mistake. However, quantum computers with full-scale error correction are still a long way from becoming a reality. To maximize computational performance, even from today's early-stage quantum computers, Fujitsu is developing a technology called star architecture in collaboration with the University of Osaka. We focus not only on hardware and platform software, but we are also putting our efforts into developing algorithms and applications. As technologies and the environment surrounding quantum computing continue to change rapidly, accurately predicting the direction of its development remains a challenge. In light of this, Fujitsu is pursuing research and development at every layer of the technology stack. By accelerating the real-world use of quantum computers, we aim to apply them to advanced computations that have so far remained difficult, including quantum chemistry and complex systems. In doing so, we will contribute to solving pressing challenges facing society and industry. Promoting digital transformation across society.